the internal sum of a triangle will be equal to, that is sum of internal angles of a triangle will be equal to 180 degrees, where the deviation is actually minimum. This particular point is known as angle of minimum deviation. The light rays from the objective lens will form an image like this, and this h is nothing but the height of the image formed for the objective lens. Hey all, I am Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, and we were dealing with optical instruments and their optical illusions. So we'll get right onto it. So today we'll see what happens when light passes through a prism. So automatically we know that when light enters from one medium to another medium, it automatically undergoes the process of refraction or just simply the bending process. So when it enters into the prism, automatically the light is being bent. So how much is this bend compared to the initial path it should have taken? Like how much is it bent from its initial path? This particular bending inside this particular prism is known as deviation, and we will be measuring how much this particular light is deviating inside a prism. So basically this derivation is to find what is the minimum deviation that can be expected inside a prism. So again, the way the light deviates is that first it will decrease and then gradually it will increase. So if we plot a graph, the nature of the graph will be like this. That is, first the angle of deviation will decrease to a minimum value that is known as angle of minimum deviation. From that value, now the angle is going to increase or the deviation is going to increase. So this is known as angle of minimum deviation, and this particular derivation is known as derivation for angle of minimum deviation or simply refraction through a prism. So first things first we draw a diagram. So what happens when light enters into a prism? When light, that is the incident ray, enters into the prism, it undergoes a bending process. So this is the path that light should have taken, but since refraction exists, it is now being bent and it is coming out of the prism. So this is the emergent ray and this is the incident ray. Now, the incident ray makes an angle of I1 with the normal. So this is the normal and it makes an angle of I1 with the normal. And again, this is another normal with respect to the emergent ray and it makes an angle of I2. It's theta, I'm calling theta as I2. So it makes an angle of I2. So if I join together all these different lines, that is if I extrapolate the line of the incident ray like this, and if I extrapolate the normals, then and extrapolate the emergent ray, all of them seem to be meeting and it is forming a quadrilateral, right? A four-sided figure like this. Let's say that it is QMRN or QNRM. So QMRN is a quadrilateral inside this particular prism. A mathematical geometrical structure exists. Now, why we are taking this mathematical structure or simply this geometry is because we have to prove a relation between these incident rays and this incident ray and emergent ray. And using that, we have to find the angle of minimum deviation. That is why we are considering this particular geometrical structure. Before going into the QNRM quadrilateral, first we will be considering the bigger quadrilateral, that is including this particular prism angle. Okay, so this particular angle which is known as angle A is also known as angle of the prism. So we will be considering this larger quadrilateral first and then arriving at an equation. So the equation we already know is that if I add up all the interior angles of this particular quadrilateral, then the entire sum will be equal to 360 degrees, right? So if I consider the quadrilateral AQNR, then I can say that angle A plus, angle Q plus, angle N plus, angle R will be equal to 360 degrees. So that is the mathematical proof. I can't explain why it is 360 degrees in this particular lesson. So again, so we can say that all the interior angles will be equal to, the sum of all the interior angles will be equal to 360 degrees. And remember, this particular angle A is known as angle of the prism. Why it is so important, you will see at the end of this particular derivation. Now, the second result we can definitely say is that angle R plus angle Q is equal to 180 degrees. But sir, how do you know it is equal to 180 degrees? It's fairly simple because this is a normal and this is also a normal, which means the normal makes an angle of 90 degrees with the surface, which means that this particular angle and this particular angle is simply 90 degrees, which means the sum of these two angles will be equal to 180 degrees. That's it. Then automatically the only remaining angles, that is angle A plus angle N, will be equal to angle A plus angle N will also be equal to 180 degrees, because their sum should be equal to 360 degrees, right? So automatically these two angles became 180 degrees, that is 90 plus 90. Similarly, these two angles also should be 180 degrees. So that is first relation we are going to find. Next thing what we are going to do is that we are going to consider this small triangle that is here. That is triangle QNR. So considering triangle QNR, I can say that N plus R1 plus R2 is equal to 180 degrees. That is angle N plus angle R1 plus angle R2 is equal to 180 degrees, because the internal sum of a triangle will be equal to, that is sum of internal angles of a triangle will be equal to 180 degrees. And don't worry where I got R1 and R2 from. I just arbitrarily took it as R1 and R2. So this will be equal to 180 degrees. Now, this will be of use in the coming steps also. That's why I'm saying it right now itself. This particular angle, that is angle AQN, this entire angle will be equal to I1 because it's opposite angles. So in this figure, we can say that this particular angle will be equal to I1 since it is the opposite angle, which means this particular angle, whatever it is, it will be the same here also, which means that is, if this is the case, this angle will be equal to this angle, right? Which means that whatever this angle is, this angle will also be same, which means if this is I1, this also will be I1. But in this case, I have cut out a small portion of this angle and said that, okay, this is R1 because it belongs to a triangle just below. So I can say that the remaining angle, whichever is there, is now I minus R1. I minus R1. Similarly, I can say that at the other end, it will be I minus R2. Okay, it will be I minus R1 and I minus R2. Why this is of effect, you will see in the coming steps. Okay, so first let us get back to our triangle. So we have one more relation which states that N plus R1 plus R2 is equal to 180 degrees. Now, why is it of use? So if I name this as equation number 1, and if I name this as equation number 2, then I can compare equation 1 and equation 2 and simply say that, okay, right hand side is equal, which means I can equate these equations, which means I can simply say that R1 plus angle R2 is equal to angle A. So R1 plus R2, that is these two angles will be, the sum of these two angles will be equal to angle A. Now let's put it as equation number 3. Now again, we are going to consider the third triangle, that is this particular triangle QMR. So triangle QMR. Now, considering triangle QMR, we already found out the angles, that is I minus R1 and I minus R2. Again, in this case also, why we found out these two angles is because we are going to find out what this angle is. That particular angle, this particular angle indicated by delta. So this is actually delta. You might have seen the capital delta like this. This is the smaller delta. This particular delta indicates deviation. So deviation is actually indicated by this particular symbol, that is known as delta. So again, in order to signify deviation, we are using a geometrical relation. So in this particular case, if I consider triangle QMR, I can say that delta will be equal to I minus R1 plus I minus R2, which simply means that sum of the internal angles will be equal to the external angle. So we can just say that angle I minus R1 plus angle I minus R2, that is I1 and I2, will be equal to angle delta. So again, if I rearrange this equation slightly, I can just simply say that I'm not using the angle symbols because it is understood in itself. So I don't want to complicate the equation even further. So it should be understood that these are angles. So again, if I take all the I terms together, then I can say that I1 plus I2 minus R1 plus R2 will be equal to delta. Right, I only took the I1 and I2 together, R1 and R2 together. So if I re-multiply it, I'll get the same result. There is nothing wrong in this. So again, if I do this, I'll get this result. Now I'm calling it as equation number 4. So let this be equation number 4. Now we have 4 equations. Now what I'm going to do is that there is an R1 plus R2 here. So I'm going to substitute 3 in equation 4. So 3 in equation number 4 implies that I1 plus I2 minus angle A is equal to delta. Right? Or simply delta plus A is equal to I1 plus I2. We have this particular result. Let's call it as equation number 5. So we'll call this as equation number 5. Up to this point, I hope everything is clear. It is just a geometrical analysis. Now, again, we are going to consider a graph. Before I told you that when a ray of light enters into a prism, it bends or it suffers from deviation from its original path. So if I plot this into a graph, I'll get a curve which is decreasing first and then increasing. So I'm going to draw that particular graph and compare the results. So this will be the nature of the curve, and I can clearly say that, okay, this particular point where the deviation is actually minimum, this particular point is known as angle of minimum deviation. This particular x-axis is nothing but angle of incidence. So this will be angle of incidence versus this will be the deviation curve, and this particular point is known as angle of minimum deviation. Okay, so angle of deviation is indicated by the Greek letter delta, and angle of minimum deviation is indicated by the capital letter D. But again, this will be the nature of the graph. I'm just reminding you. So the important thing about this particular graph is that there will be a point where two values actually coincide, which means that the incident ray will be equal to the emergent ray, or simply I1 will be equal to I2. I1 will be equal to I2 at a particular point. That particular point is known as angle of minimum deviation. That can be analyzed that way also. But simply what you have to write here is that first you have to consider curve of angle of minimum deviation and angle of incidence. So you're going to consider the curve of angle of minimum deviation, that is this particular curve, against angle of incidence. So if you consider that particular curve, we have certain results. That particular results are delta becomes D, that is angle of deviation becomes angle of minimum deviation. It is indicated by capital letter D. And R1 becomes R2, that is both the refracted rays are parallel to each other. That is, both of them are parallel to each other. If you observe the figure, you can see that R1 is equal to R2. So then we can say that R1 will be equal to R2 because they are parallel to each other. That is, this is the first refracted ray and this is being considered as the second refracted ray. Both of them are parallel to each other. That's why we are saying that they are equal. Okay, if R1 is equal to R2, then I can automatically say that R1 plus R2 is equal to A was the result we had. If R1 is equal to R, let's say R2 is equal to R, then I can say that 2R is equal to A, or simply R is equal to A by 2, right? Then from equation number 5, it states that I1 plus I2 is equal to A plus delta. So instead of delta, I can actually substitute D there, that is angle of minimum deviation. Then I can say that I1 plus I2 is equal to A plus D. Again, remember here D is nothing but angle of minimum deviation. Again, I told you at the point of angle of minimum deviation, I1 will be equal to I2. So when I1 is equal to I2, I can say that 2I will be equal to A plus D. Right, I1 is equal to I2. Let's call it as I. Then I can simply say that 2I will be equal to A plus D, or simply I will be equal to A plus D by 2. Right. Now, we did all this to find an expression for incident ray, or simply in terms of I, because now we are going to apply what is known as Snell's law. So from Snell's law, we know that sine I divided by sine R is equal to N21, or simply N2 by N1. So again, we have an expression for I, we have an expression for R. We are going to substitute these expressions into this particular equation, which then will imply as sine A plus D by 2, sine A plus D by 2 divided by sine A by 2, sine A by 2 will be equal to N21. So this is the equation in order to find out what is the relation, or simply what is the relation between angle of minimum deviation and prism angle. So this particular A is actually prism angle. If you are asked to find out a relation or simply express the angle of minimum deviation considering the curve of angle of minimum deviation versus angle of incidence, you have to derive this particular result. But for angle of minimum deviation, mostly numerical questions are being seen, but again they can ask for the derivation also because it is very important. Now again, moving on, we have the applications of ray optics, or simply the optical instruments we have been talking about. And the first optical instrument is a microscope, and simply it is a simple microscope. So what exactly is a simple microscope? A simple microscope is more of like a magnifying glass. That is, you might have seen that carrot readers or some other palm readers and all that will use this particular viewing glass in order to view the lines in your palm or read cards for your future. They will just hold this and see things much more clearly. That particular arrangement is known as a simple microscope. But before getting into the topic of simple microscope, you need to understand one thing that is known as near point. What is near point? So near point is just the closest distance through which your eyes can focus light onto your retina. That is, if you're reading a book, the closest you can keep that book without blurring or straining your eyes is known as near point. And generally for human beings, it is almost around 15 to 20 centimeters. Generally it is 20, but for younger adults, it is 15 centimeters. As you get older, the elasticity, the collagen varies and you lose that particular near sight. So near point is nothing but the closest distance for which the lens can focus light onto the retina is known as near point, and generally again it is considered to be 20 centimeters for adults, and for children it is around 15 centimeters, but that can vary according to individuals. But in your textbooks it is given as 25 centimeters. So for a perfect adult it is around 25 centimeters, but again this particular result can actually vary. You can also do this particular experiment using a simple scale and a notebook. Now getting back to the ray diagram of the simple microscope, we can see here that how a simple microscope functions. The basic principle it uses is that if you keep an object in between the focus and the lens, automatically that particular figure will be enlarged or it will be enhanced, it will be magnified. It is exploiting that particular principle and it is enhancing that particular image. As you can clearly see here, the object is placed in between the focus and the lens, which means the object will be enhanced. So the image is formed far apart here, making our eyes or tricking our eyes into believing that, okay, the object is now large. So that is the only thing that is happening here, and this is the ray diagram for that particular simple microscope. So for a simple microscope, the image formed is actually virtual and erect. Because this image is not real, it is virtual and it is erect. It is not inverted, it is erect. And we already know that magnification M is equal to V by U for a lens. So we know that V by U is the magnification for a lens. But now instead of writing V by U, I am going to write it as V into 1 by U. Right? M is equal to V into 1 by U. I can write it like this also. But I do know one more equation, that is 1 by V minus 1 by U is equal to 1 by F. So substituting that particular equation instead of 1 by U, I can rearrange the equation in terms of focus and I can say that, okay, instead of 1 by U, I can write it as 1 by V minus 1 by F. So 1 by V minus 1 by F. Now I am going to open the bracket. Now if I open the bracket, it will be V by V minus V by F. Or simply this will be equal to 1 minus V by F. So this will be the magnification of the simple microscope. And again, if you're measuring something, since it is a microscope and you're trying to see that particular figure very close by, then again, instead of V, that is image distance, we are going to apply the near point, which is indicated by the letter D. Whatever the explanation for near point I gave at the beginning of this particular derivation, we are going to use that concept, and instead of V, we are going to use D. So V will be equal to D, which is nothing but near point distance. And again, this D will be negative since it is on the left hand side. So again, since image is formed on the left hand side and it is formed at the near point, we are going to say that, okay, this now transforms into 1 minus D by, that is minus D by F, that is 1 plus D by F. This is the final equation for the magnification of a simple microscope. And again, one more thing is that if the object is really far away, mathematically at infinity, then the only difference is that this 1 will be avoided and the equation will be simply D by F. That is one exception. They can ask you that is simply, what if the object is in infinity? Then automatically 1 plus will be eliminated and simply d by f will be remaining there. So this is the equation for a simple microscope, but the only limitation of this particular simple microscope is that it can only provide you with a 9 times zoom. That is, it can only magnify the object 9 times of its original capacity. Maybe that is not enough for you, because if you're working in the medical field and if you want to see red blood cells or something, you can't use a simple microscope, right? For that, you have to use a compound microscope. So automatically, the next optical instrument we are going to see is a compound microscope. So here is the ray diagram for a compound microscope. So here there are two lenses being involved. So the first lens is known as objective lens. So this is objective lens, and this particular lens is known as eyepiece lens, or simply eyepiece. So there will be an objective lens or object lens, there will be an eyepiece lens, and these two lenses will be kept apart a distance of L. This L can be different according to the different microscopes you are using, but this is the general theory. So these two lenses will be kept at a distance of L, and again FO is nothing but focus of the object and FE is nothing but focus of the eyepiece. So focus of objective lens, and it is the focus of the eyepiece. Focus of the objective lens and focus of the eyepiece. So you can see here that the object is now forming an image which is real and inverted. So this particular image is now going to be acting as the secondary object or second object for this particular lens. That is, however, we saw the derivation in the previous topics, that is previous sessions, we saw that one image of one particular lens will be acting as the object for another lens. Just like that, compared to this lens, now this is the image. But when we are doing for this lens, this will be acting as the object. So again, here the image is formed which is inverted. Now this will act as the object for the second lens, and that will be enlarged since it is in between the focus and the lens. So that will be enlarged, and that particular figure is the figure we are seeing when viewing through a compound microscope. Again, the symbols have their usual meanings, which is object distance, image distance, and FE is nothing but the focal length of the eyepiece. So here the points to be noted is that the image formed is real and inverted. The image formed is real and inverted, and this will act as the object for the second lens or second lens, which is called as eyepiece. And then again we are going to find out again the magnification. So magnification M will be equal to, since there are two lenses involved, remember combination of lenses, it will be not M, it will be M1 into M2, or simply M1 times M2. Or we can write it as MO times ME. That is magnification of the objective lens times magnification of the eyepiece. So again, MO will be equal to V by U. And again we can say that, okay, that is approximately equal to the focal length of the objective lens. So we can say that U is approximately equal to FO. That is focal length of the objective lens. And we can say that this entire V is approximately equal to, again this is for just demonstrative purposes, these lenses are not that far apart, and this object formed will be much more closer, which means that this V is almost approximately equal to L. So we can actually take V approximately equal to L also, and substitute in the results, which means that MO will become L by FO. And similarly for ME also we can say ME is same as that of a simple microscope. Whatever we derived in the previous derivation, the same thing, because it is just one lens and this is acting as the object. It is just being enhanced. So we can say that, okay, ME will be equal to 1 plus D by F. So this will be equal to 1 plus D by F. So again, this implies that MO times ME will be actually equal to L by FO times 1 plus D by F. So this will be the total magnification of a compound microscope. The only difference here is, again, if the object is really far away, then you don't have to consider this one, then it will be D by F only. Here also there is not much change. So again, in the case of a telescope, we can say that this is how the ray diagram will be and how the image will be formed. Similarly, since the object is really far away, for a microscope it is very close by, right? But for a telescope, the object is basically really far away. You're observing stars, planets and sun, moon, like that, satellites and all that. So the object is really far away. So we have to use a lens with a larger curvature. Again, the figures are only there for a demonstrative purpose. So what will happen is that the light rays from the objective lens will form an image like this, and this H is nothing but the height of the image formed for the objective lens. Now this particular image will act as the object for the second lens, which is known as the eyepiece. Now, since the image formed again is in between the focus and the eyepiece, that is the second lens, the image formed will be enhanced. So automatically the image will be larger or magnified. So again, you will get a larger magnified image. The image formed will act as object for the second lens, which means whatever image is formed here will act as the object for the second lens. And again, here we are measuring angular magnification, not directly magnification. We are measuring angular magnification since it is a telescope. So how we measure the angular magnification is that we will be considering these two angles, that is alpha and beta. You don't have to go into the details of how these angles are obtained, why angular magnification and all that. But for a telescope, just know that angles alpha and beta are considered, and then we can simply say that the magnification will be given by m is equal to beta by alpha. So again, in order to find this relation, we are going to find what is tan alpha. So tan alpha means that we are going to consider this particular triangle. So we are going to consider this particular triangle here. So if you are considering that particular triangle, then you can see that tan alpha will be equal to h by FO. Again, since the angle is going to be really small, we are going to approximate tan alpha to alpha, which means alpha will be equal to h by FO. And similarly, we are also going to find out beta. We are going to find out beta, or simply tan beta, tan beta will be equal to, that is for this particular triangle, then we can say that tan beta will be equal to h by f. Similarly, tan beta will be equal to h by fe simply, and then we can say that okay, beta will be equal to h by fe. Now we are just simply going to find what is beta by alpha. So again, if we take beta by alpha, it is very simple. You can just say that it is going to be the ratio of these two, in which the h's will cancel out, and simply you will get FO by FE. So you will get FO by FE. This will be the final ratio you are going to get. That is focus of the objective lens to the focal length of the eyepiece. That particular ratio will give you the magnification. So how far or how closer they are, it will define the magnification. So these kind of telescopes are actually known as refracting telescope. It is known as refracting telescopes. So the problems with refracting telescope is actually that chromatic aberration. Chromatic aberration and maintenance and finally manufacturing lenses with larger aperture. So larger aperture is also required. So all these are disadvantages of a refracting telescope. In order to avoid all this, we have a new kind of telescope that is known as reflecting telescope. So reflecting telescope, or simply cascade telescope, actually fixes all these errors and can be used much more smoothly. So again, what is chromatic aberration? Chromatic aberration just means that different kinds of wavelengths or different frequencies are actually refracted at different rates, which means there will be a shift in colors. So this actually is known as chromatic aberration. Chroma means just color. Aberration means a fault in that. So we can just say that there is a color correction. That is, you cannot actually see the object for what it actually is. So that chromatic aberration is present in refracting telescope. But if you use a reflecting telescope, you can actually avoid that. So again, if you are using a reflecting telescope, that is, instead of a refracting telescope, if you are using a reflecting telescope, then automatically you can fix all the disadvantages of that particular telescope. It also fixes not only chromatic aberration, but it also fixes spherical aberration. That is because of the shape and size of that particular lens. Now here you can see that it uses reflection in order to work. So this type of telescopes are also known as Cassegrain telescopes. So with this, we are finishing our ray optics and optical instruments chapter. So we have officially finished ray optics and optical instruments chapter. I hope you have understood everything in this particular lesson that is being discussed. And I'll see you all very soon with a new chapter. Until then, thank you.